let's go ahead and get started for today. I'm going to go and review a couple more with the gates because we forgot to actually do our analysis of how we could do this using transistors, so everyone can see how we build everything together. Then afterwards, we'll finish up the slides, which is going to be a general overview of basically everything we're going to go into, memories, which was really the next step, and then a little bit about processors. And then after that quick, outline, we'll actually go into our first memory unit, which will be a latch and a flip-flop.
Whoa.
Yep.
Fancy.
It's a little cold for flip-flop.
Totally. No, not at all. Good try. Good try. Okay, so the inverter. Does anyone remember how we can build an inverter with the transistor we created? Does anyone remember what the transistor looked like? No? Okay. Wow, okay, maybe we're not going to have a picture then. So here's a transistor. So we'll say that the input is, of course, the gate to the transistor, of course. Ground, aka the sink or the drain. And then O is the output, where we want O to be the opposite of what input's going to be. Good morning.
Good morning.
Do you remember what we could do with this transistor to turn it into an inverter?
Maybe like flipping the output and then making the other one the drain or something like that.
Closing the gate?
So, remember, the gate is going to, so let's see how to put this. I is the input, aka this side of the truth table. So if I is 0, the gate is not going to connect, which means that the output and ground are going to have high resistance.
Can we just invert the output?
Right, so how do we invert the output? That's what I'm saying. This is what we want to happen conceptually. How do we make it actually happen using the transistors that we have developed so far? You know, this is the theoretical concept. How do we practically do this? Well, we're kind of, in a way, we got one of it, right? If the input is on, it's pushing, then it would be automatically connected to ground, so then it would just basically flow to ground, and then output would be low voltage because the input's going straight to ground. So we got that. But how do we get the output to be high voltage in this one?
You push the transistor on it, right?
We push the transistor on it. I don't think I understand what you're saying.
Never mind.
Okay. I was totally wrong. All right. I guess quick review. If we apply voltage to the other side, basically what happens is if I is not connecting, then the voltage does not connect to ground, and then output is going to have high voltage because, of course, you're pushing voltage that way. On the other hand, if the input is pushing down, then it's going to connect a circuit, and it's usually safe to assume that the voltage is going to take the least resistance because usually output's going to have some more resistance down the line, so then it's going to go ahead and flow in that direction. Usually you do put a resistor in here just to make sure that it doesn't have high voltage. All right, does everyone see how this is working? Any questions or comments? Because we're going to start building these for the other gates using the transistors, and I'm going to stand in the back of the room asking you to do it. But I will do one more for you before I do that.
Okay.
All right, the negated NAND. Notice this time you have 2 inputs and only 1 output. So usually you're going to have the inputs be part of the transistors. So notice here that we have 2 transistors connected in series to the output. Notice with the easiest way to look at this is look at the truth table. Namely, if any of them are off, not connected, you want it to be output. So really you're just taking an inverter and putting 2 transistors and saying that unless they're both connected, there's going to be high resistance on this side, which means that the output will be 1. But if they're both connecting, then the electrical flow will want to go to the ground, and then that'll give you the 0. All right, everyone good? Notice we just got negated and using 2 resistors. One thing I want to also mention is assuming that a transistor takes one time unit, we'll just say 1 picosecond for the sake of argument, to saturate. How long does this whole circuit take to saturate?
You count the resistor on the voltage.
No, the resistor's instantaneous.
So 2.
So you say 2. Why do you say 2?
Because you have 2 transistors and they're in series.
They're in
Not-
series.
They're not in series. They're in in series.
Series.
Yeah.
Yes, but do they saturate one after another or in parallel? Right, so if they're both saturating in parallel, then it's really just
okay.
one, right?
Yeah.
Right. Yeah, I know. It's tricky. That's my point. No, that was good. That was good. This is tricky because now you have to figure out what's happening in parallel and what's not. There is a ton of parallelism in this course. All right, great. All right, guys, it's your turn.
If you don't know, just guess parallelism.
Yes, parallelism.
It's gonna be a purple thing.
Well,
I'm
I'm just
gonna-
gonna take a guess and say it's gonna be 2 transistors.
Oh, here we go. You know, we got markers and a board.
Oh my god, we get to
Come on.
write on the board.
I know. It's going to be awesome.
We get to write on the
I
wall.
we still saw that video where I ran up and had to erase something.
So I'm gonna go ahead and draw this on the board. I don't know why that was a B, but it was. That was the best B ever.
A line. Why is it so tall?
Why
Why
is
is
everyone
it
a
tall?
critic? All right, and then sure. Well, hey, look at this. I get to just copy it. Oh, that's beautiful.
Copy pasta. I think he's gonna turn off the projector.
How'd you
So
know?
you
I
can
think
draw.
so too.
Yep.
Yep.
I was explaining for Caitlin because she looked really confused.
Y'all ready for this?
Your lines.
Oh, that's too frustrating.
Oh, look at that glare.
Oh, there we go. There's still a glare.
That's okay.
All right,
It always
guys.
happens.
I'm going to put this right here. And I'm going to stand back here. Okay, I told you.
I did not say that.
All right, Alex, you said you had an idea. What was your idea?
Well, I'm horrible at drawing, but if you want to.
That's okay, as long as you draw boxes that at least somewhat represent a box.
You can draw a somewhat rectangle.
And I'm left-handed, so
Well-
that just makes everything harder, right?
It's an AND gate, right? So you can do
Sure.
2 transistors. One transistor, next transistor. Same as that last setup for the NAND gate.
Careful not to
Except
go
take
too
away
far
the
over.
voltage on that side.
Too
and
far
put
over?
an extra ground
It's
on
too
the
far
side.
over.
Yeah, I think you're too far over.
And then
It's
back
okay.
that way,
Just
and
keep
it's
going.
like-
We're gonna.
I would never
we're
see
gonna
it
go
drawn,
with the-
sorry.
All right, and then this is like that little,
Sure.
right?
Sure.
And this is
Put a
that.
little box above. Okay, yeah, that'll work too. All right.
Okay, we getting somewhere?
Candle.
Yeah, I'm following you so far. I see 2 transistors.
2 transistors. All right. And we probably want this wire connecting them, right?
Okay.
Whoa. We're
Alright.
getting places.
Do label where you want A and B to be.
Okay, so you call this one A, you think, y'all?
Yes, that's
Y'all?
fine.
Okay, all right.
Do you want A to apply to the input?
Input right here.
Yeah, that's the input. Because that's saying. Okay, hold on.
Huh.
Remember, A and B are inputs. I know when you're at the board, everything's confusing.
All right, there we go. A and B.
All right, okay, now that
They are in parallel.
All right, okay.
So
All right, now remember, Y is the output. So where's Y coming from? We're going,
let's see.
whatever.
Where do y'all think I should put the output? Somewhere over here.
Yes.
Yeah.
Just do like a wire.
line.
Yeah, yeah.
Yeah.
I really like wires.
Wire.
Oh, that's a
That's
cute
a-
little line.
How's that?
Squiggly line.
Okay, where's
Squiggly
ground?
line. You
Where's
want
ground?
You need ground.
ground right here?
that-
No,
well,
that's
you
on
could.
B. You need ground on A.
Ground on A, right?
Left side A.
Yeah. Okay.
Yeah, you can put it in.
I knew it was on one of these sides. I
It worked once.
Sure,
Ground.
that sounds great.
Woo!
Okay. So we've got ground. We've got output Y.
All right, so
Got
let's
A
run
connected to
our.
B.
So now, if A is 0 and B is 0, output 0. That's correct. If A is 0 and B is 1, the output would then be 1, because what's happening is you're applying voltage here for B, because that's what B is. It can't go this way because A is disconnected, so it wants to go this way, which makes Y high voltage.
So this one is correct as well?
No.
No, it's incorrect because Y, you want Y to be 0, not 1.
Ah, okay. So we need this to be negated then.
Okay, so, we'll add a negation transistor.
Isn't that something like?
Squiggles.
That's a resistor.
Is that what we want? No.
No.
What do we
Well,
want?
if you're going to apply voltage, yes.
Okay, that's what we want for voltage. What's the negation thing? How do we?
Is this also being recorded?
No, it's
Yeah.
it's right here. It's like somewhere over here. You gotta add like the.
Is it just the VCC and it will make
Okay, so
it
you're thinking
backwards?
beforehand where we added voltage somehow?
Yeah, that's
Okay, so draw your resistor where you had it. Now I understand what you're asking for.
Mhm.
And then have it go down and just type it VCC.
Type.
Whatever.
like VCC.
Type VCC. with
So
your hand.
now what that does is it says if
Okay, so now, so now if A is applied, actually, now you're always going to be on until both A and B are applied, which would be 0. So you actually have the exact opposite of what's on the truth table, which means you're actually very close. Because
Negate.
That's the NAND gate, right?
that's the NAND gate. We're asking for the AND gate.
And so invert.
Maybe the opposite of that.
What can we add to this?
A circle.
We can always add circles, right?
Once again, true.
is the answer like obvious and you're just like waiting for us to catch it?
Well, I mean, I've done this so many times, so to me.
It's obvious to him.
Okay.
And also the other thing to keep in mind is there are many correct answers.
Many correct answers.
Oh gosh, no.
Transistor, not,
Yeah, transistor
yeah, like in the middle.
in the middle. Okay.
I know that sounds weird.
So you're saying add another transistor for the middle?
Or not the middle, maybe like on top of the other one.
We're definitely going to need another transistor.
Okay.
That was
Alright.
illustrated.
So would you guys want to put it like after this output here, or would you guys want to put it here? You think?
Tiny box in the middle.
Tiny box in the middle. All right.
Well, that way we're not going completely off the
No,
screen.
no, wait. I think we should put it. We should probably maybe put it at the output because what we're gonna need to do is have the transistor be like so created so that way it's an inverter because
Because we've already got the desired
Yeah.
output.
right. So we've got basically
We've already got the
everything.
desired
We've got
But
because
We
we've
might as
got
well
the
add one to
opposite
the
of the
end.
output we want. So to get the output we want, we need an inverter. So we need
Which-
to put the transistor at the output.
Yes.
Which makes sense. So I'm gonna go ahead and do that. We got our output.
We're gonna have to lift the camera.
What's that?
So we're gonna have to lift the camera.
We'll show everyone after.
Show
it's
everyone.
over.
Yeah, sure. We'll see how that's doing.
Oh, it's completely off the
Oh,
screen.
I believe it because I'm all the way over here. It's just, I'm writing.
You're doing great. Keep going.
All right, so we're gonna connect. This
First one.
here. This is now going to be Y, and this is no. This isn't connecting here. This is connecting here. Right.
why don't we do that? and
This was Y coming from there and going into the input there, right?
Okay.
And then we've got our output here, but we need something here to invert this.
Well, because you're gonna have ground on the left side,
We're gonna have a ground here.
right? So whenever like that input is activated, like it's gonna go to ground.
Okay. And why? I'm going to help you out because what you're saying and what you're doing are different. Why? Yeah, should be at the very end.
Yeah. I was just saying that this is where the original Y was coming from.
Sure.
But yeah.
So we'll put Y over there.
At
Y,
the-
I can. Oh, okay, great.
Yeah.
Awesome. All right, let's take a look at this. Okay.
So now we've got the ground, and
Okay.
are we missing something still?
So what's going? Yeah, go ahead.
Oh no, I was just thinking. Okay, so when it's high coming out, going into that transistor,
Yeah,
what are we? We are making it low.
So one issue you have right now with your drawing, sorry to interrupt, John,
No, it's okay.
is that the input to your second or your last transistor is pretty much always on because you're applying voltage there.
Oh, right.
I don't think you mean to apply voltage at that spot.
Okay,
Just
so
move it to the corner.
apply it to
The left.
here.
Okay, sure.
Okay.
Keep this one because we still need a ground, right?
Well, you should.
Wait, why would? Oh, you're
Shouldn't you
Yeah,
have?
I thought if you applied voltage to the other side, then it would always be on.
No,
That's
if you
when we
connect
take
it
your
directly to ground and then it goes on.
Oh,
Because
okay.
you always
Okay.
assume later on there's going to be resistance.
So I'm gonna switch this
It's
up.
not the
though.
easiest way to understand.
We still need a ground though, so I'm leaving the ground where it's at, right? We all agree we need a ground still, or no? Do we need
I like where your ground is, and I
Yes.
like that input going into the next transistor. So that was working, because I know which solution you're going to.
Oh,
So
back
you-
where it was.
So this was good.
Yeah, that was good.
Okay.
The problem is where
This
you're,
one wasn't good right here.
well, the problem is where you're applying voltage. You don't want to apply voltage there.
Oh,
Oh, apply it all the way to the end.
the
Yes.
VCC.
Okay, just move your VCC over.
Yeah.
Yeah.
Squiggly.
Oh.
Yeah, because you're applying it between those two transistors. That
Yeah, that, I got
you're
it.
always
I
going to
got you, I
have
got you.
on, no matter what.
Yeah.
So,
So we're gonna do something like this here then,
all right, here we go.
Squiggles.
and then.
Okay.
Yeah.
Ta-da.
Great. I think this is going to work. So basically coming out of here, these are all going to be, the only way you're going to have connection going this way is if they're both on. And if they have a connection going this way, then that'll be on and send this guy to ground, which will make him, wow. Hold on a second. Sometimes I even get confused. Let's start at the beginning. A is 0, 0. Don't apply, nothing's connected. So this guy's not connected to ground. And we,
Until we apply voltage. Because it's gonna be 0 most of the time until
So we're
this
having-
one is connected and apply voltage, and then we get our output, which is right
maybe you had voltage in the right spot. What's the last one? 1, 1. So if you connect both of them, then that's connected, so then that'll be 0. I think you actually, did you have voltage in the
I had it right here.
No, you had it right there. That's where it was supposed to be. I lied the whole time.
Oh my.
I'm so terrible.
Such
what I
a
was
terrible
talking about.
person.
Man, what am I thinking?
Because I thought if you had it at the end, then it would make it
Yeah.
cut on.
Yeah, hurry up.
Oh,
Yeah, everybody fix this.
Computer scientists.
Whatever. Off
It's
by one.
fine. We're trial and error.
Off by
type.
one error. It's okay.
Crazy.
It's close enough, everyone.
All right. Yeah, so now, well, you probably won't have the resistor right here, but we're going to ignore that for now.
We're not gonna put a the.
Right, so now if you have nothing and nothing, you're applying over here, which of course makes it 0. Okay, that's great. And then, oh, you have VCC. Oh, so you do want, that's the trick.
Do you want 2 VCs?
Yeah, you want. That's
Alright,
the
so
trick.
That's what I
Well,
thought.
that's what we said originally.
Yeah, that's what you said originally. Now that makes sense.
Okay.
that'll
yeah,
connect.
that makes
Yeah.
more sense.
Now that makes more sense. Okay. So nothing, you're having voltage applied here, which sends it back to ground. Great. 0 and 1, again, voltage being applied, sends it back. 1, 0, voltage being applied, send it back. It's 1, 1, voltage going to the ground.
So voltage coming this way, going to ground, and
And
voltage
then-
coming this way, it pushes it back instead
So
of.
that last voltage is our 111.
Yeah. Okay, so then that actually checks out the truth table. Do y'all see what's going on here? I know I kind of got a little confused. Good. All right, now what's the saturation of this? That's gonna be a little tricky here.
Well, anything happens
2
on the
picoseconds.
transistor side.
Why do you say 2?
Well, the NAND gate was 1 and converter was 1, so
Okay.
you get 2.
Yeah, so you got 2 of them. Yeah, you have to keep in mind that these have to saturate before this input's correct, and then that last transistor saturates. So while these two can happen in parallel, this one is waiting for the output of these two guys. So we're going to say it has a cost of 2. Now notice that a NAND had a cost of 1, but just a regular AND had a cost of 2. So that's a
Very
little...
inefficient. Seems very inefficient.
You're
Right.
efficient.
Ouch! That's why a lot of circuits are built out of NANDs or NORs, as we'll find out. We can do the same thing with NOR. Okay, where are my slides?
We lost
Not on the projector.
Apparently. All right, now we get to do the OR gate.
Erasers.
My hard work.
I know. It's gone.
Oh no.
It's like a bullet right here. Well, they're all bullets. This is the... Wow. Let me-
Gorgeous.
Oh, that was
No,
terrible.
no, no,
Star
no.
Trek symbol.
It's the Star Trek.
Yeah, it's the Star Trek
It's the
symbol.
Star Trek.
Turn to the side.
All right.
It's okay.
It's like a really sad moon.
I'm glad you're our critic. All right, who's next?
I'd like to see you do better.
Yeah, here you
Yeah,
go.
Caitlin, there you go.
You volunteered yourself. Congratulations.
So boxes. That's fun.
Okay.
If you always start off 0, 0.
Let me guess, we're gonna need another transistor.
Yes.
Yay. More boxes.
Dun, 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 dun.
Yeah.
Okay. I don't know where you're going right now, so.
I don't either.
Oh. All right. Anyone have an idea here?
Well, I don't know if A and B should be connected as much, considering that it's just an OR.
Oh yeah. How would you do that with an OR? Since would it be two separate lines? Because
Oh, you're saying you're trying to
I would think one step at a time. Think a NOR gate, because that's going to be the first section, and then the last step is just going to be inverting the NOR gate.
Okay, yeah. Hold on 1 second. Let me give you a huge
yeah, I
hint
don't remember the NOR gate.
so y'all don't get confused. You are never allowed to do this. That's bad.
Made a
Not only does it kind of look like the flux capacitor, but the other problem is when you do this connection, that means that A can then try and backfill B, which is not good.
Yeah.
Your circuit is going to end poorly. So you can't do that.
Okay. Still don't know where I'm going.
Because otherwise then war would be really easy. Just connect the wires, we're done.
Nice. Okay, so do we need to have them separated since it's an OR,
A
or
and B at the same time.
to have like B down here?
And it's
I don't remember what the NOR gate looks like, so.
Or. Oh, you have the truth table right there. You just got to make that
We're
truth
doing the
table.
OR.
yeah, so
That's why I wrote the truth table for you.
Wouldn't you just put some output then?
so
Yeah.
You just throw an output. Because if there's no voltage, it's just gonna do nothing. Otherwise, if there's voltage from any of them, it's just gonna go.
Kind of.
Why don't we just invert the
Yeah.
NAND gate?
Because then you
That's
get an
it.
AND gate.
yeah, that's an AND gate.
Yeah.
But if you think about what a NOR gate is, and then invert that, then we only have to think about just the first two transistors, and then invert on the last one. So,
Yeah.
but I'm not sure how to do this.
Yeah, I don't remember the
Start
NOR
right there at
gate.
the third transistor.
Yeah, I don't know what you're doing right now.
I don't know. Eh. So,
I mean, yeah, if you're trying, if this whole gate was just B connecting the transistor. All right, so here if we have B applied, sure. If B is applied,
But then A wouldn't be.
right, well, if B is applied, then I can kind of see the second and last one working, but not the third one.
Oh, not that?
Yeah, because if A is applied but not B, then it's going nowhere.
Yeah.
So you want them in parallel then?
We can try that. Let's try parallelism. We have an eraser if you want to save your hand.
I'm an artist, I don't really care.
Okay.
So would we need another ground here?
All right.
And then you probably need another transistor out there?
Yeah.
Temporary outputs.
And then how would we connect both of them? Would we connect it to the voltage or would we connect it to... I don't know how. He's giving me the
Maybe
face.
connect one to the ground and connect one to the input,
Voltage.
maybe?
Yeah.
Okay.
Interesting.
And then we're gonna need to negate that, right?
No, you're
Let's
just
do-
doing
let's see what
or
we
you're
got.
just
Yeah,
doing.
see what you got right now before
Well-
things go crazy.
Because this, wouldn't that be changing some voltage? Or would that just be
Okay,
connecting
hold on a
them?
second here. So apply A, and that, well, it wants to flow to ground.
Yeah.
That's the trick. But so you know, ground doesn't have to be ground. It can be voltage as well.
That could be voltage?
Yes. Maybe that's what you're thinking. I don't
know.
Like I said, well, let's try voltage there. Let's see what that does.
Do you want the squiggly lines?
Sure.
Voltage.
All right. So now if it's connecting B, it's going to flow voltage over, and if A is connected, it's going to flow voltage over. Otherwise, if they're not connected, then nothing's going to go over. So you've taken care of the 0, 0 because neither of those things are going to connect. But if one of them's are connected, one of them's on, then voltage is going to flow. Okay, great. Well, I mean, I'm assuming A has voltage connected to it as well, the top transistor. Of course. Okay.
She's just gonna update it as well.
So now, if A is applied to the input and only A is on, then it really has nowhere to go but the output. Okay, that's fine.
And then this one.
If B is applied, then sadness occurs because there's no input to turn it on. Okay. Yeah.
Could it have two inputs?
No.
No.
Do we need to add another voltage somewhere?
Try that.
Where?
Maybe.
Because if we had added one here, wouldn't it mess with us? Because it would mess with how A was running.
So maybe
Mhm.
between the B and the other transistor.
So like here?
Yeah, would that do anything?
No, because I'd just be pushing more into here, and we need something to open the gate
Something like
for B,
that.
right?
Okay, hold on a second. I think I'm thinking about this too hard. Let's go back to the truth table.
We're just trying to figure out
Right.
one of those.
Sometimes it's helpful to also look at not A and not B. So, and then we have what?
1, 0, 0, 1. Here's
0, 0.
All right. You want to know what that is?
That's the NOR gate.
It's the what?
Is that the NOR?
Not the NOR, but you're close. Isn't that the negated and?
Or negate is the.
Yeah.
Yeah, so if you negate these two first and then put a NAND afterwards, then you get the right output.
Do the what?
Negated
All right,
and.
First, negate them both, invert them both.
That's what I was saying.
I think so.
Because you just, the outputs are just, you just want to flip those outputs right there.
Yeah. Okay. Yeah.
Oh,
That's
so
your
just like
NAND gate is
so
0,
then
0,
just
0,
like
1.
add inverter gates before the inputs for an AND.
Yes.
So,
So
change
it's
this
negated,
back.
negated, and.
So change it back to the and.
Yeah. So erase that. So. Whoa. The voltage, make that ground. Yeah, no resistance to ground. You don't want to resist ground. Okay, make that an inverter.
Do the what?
Put a little resistor on the right side, connect it to VCC. Now underneath it, do the same thing for B.
So here?
Yes.
No, the other below it.
Cindy?
All right. Now have those two inputs go into a NAND.
Bless you.
So both of those go into a standard transistor. I mean,
So this is the same picture we drew before.
yeah, okay, so have A go in there. No, into the input. You want to help her?
Yeah,
You got this? So
I was the one that drew.
the board
Where's
is
that one going? 'Cause this is
into
the same.
another transistor off to the side,
What?
on the right of that transistor. Just draw a little.
Yep.
Yeah.
Oh, this is gonna be ugly.
Yeah. Okay. Now you need to connect those transistors in serial. All right.
We need a ground over here.
These are ugly wires.
Okay.
Ground
What else?
first.
All right.
Output.
Gotta doctor this up. What are we doing?
No,
that
no,
was
no,
first
that
one.
way.
There
That
we
one.
go.
There you go.
All right.
There you go.
Now,
And then the little transistors between.
you mean resistor and
In the center.
Yeah.
Oh, I thought it was right before the
and then
album.
yeah, sorry.
Yeah,
I was wondering center.
All right.
Woo!
You said in.
Okay.
That's really complicated.
Good job.
Oh yeah, they're gonna only get more complicated.
No,
Yeah.
don't say that.
I don't like it.
Okay.
Sadness.
Follow through on that? Follow
Sure, let's
through.
follow through real quick.
Oh, Cindy fat butt.
So 0, 0.
We'd have just had
This is
to-
essentially negating them, right?
Still not dominant.
So then we have A naught and B naught.
You have them moving around. Huh?
B naught.
Sat there for 4 hours.
A naught and B naught have to both be on for the electrical flow to go to ground. Otherwise, it's going to be applied.
Right, so they're
So-
both on, you get 0 with your output between 1.
Right.
Okay, first one, 1, 1, 0, 0, whatever.
Okay. So when they're both on, look at the truth table. That's why I wrote the truth table. When they're both on, then the electrical flow will go back here and it'll be 0. All right?
Otherwise,
Otherwise, it's going to be 1, which is what we're looking for.
Because only when they're both on will it go back to ground.
Right. And they're both of those are on when both A and B are 0. Everyone see that?
And the more reason we need.
Do you want me to go through each one of these and show you, or
No.
I can do one of them maybe just to help out? Sure. We'll do the middle one. A is 0.
knock yourself out.
Thanks. A is 0. Since it's not being connected, that means voltage doesn't go that way, which means voltage is going to be applied. 1. B is on, which means voltage is going to go back, so to speak, and it'll have low voltage or 0. This gate will be applied, but not that one, which means voltage is not going to go back, it's going to go forward, and that will turn it on. So for this one, it's correct. What's the saturation time on this thing?
2 picoseconds.
Why is it 2 picoseconds?
because the two inverter gates are going to, those ones right there are going to saturate in parallel.
Correct.
That's 1 picosecond,
Mhm.
and the NAND gate is going to saturate for 1 picosecond.
Right.
Yeah.
And the inputs of the NAND require the inverters to complete.
Yeah.
So it has a 2. All right. Any questions on this one before we go to the last one, which will probably cause lots and lots of sadness?
No.
What is the next one?
Probably an XOR.
He's like,
The XOR?
I'm glad you asked.
Wait. I think, wait.
You
All right.
volunteering already?
Sure, why not? Wait, is this not going to be the obvious answer?
It could be the obvious answer.
Could
So,
be.
Depends on what your obvious
yeah, it
answer is.
depends because I've had one
Depends
student
on,
come
like,
up here and
what's
it's like,
okay.
yeah, like, it's like 10 transistors. I'm like, hold on.
All right.
Go ahead.
Okay.
You want me to leave this up here?
No, yes.
No, yes.
No,
Absolutely.
yes. All
I
right.
don't know what he
The
said.
truth table up there is
So-
for,
Yeah, so
I updated it
yeah, the
because now it's an
XOR.
XOR.
Okay.
So only one has to be on, otherwise it's off. So all I had to do was
Wait a
change that
second.
last 0.
Yes.
Okay.
Just gotta change that. Okay. Ooh. Wait a second. Hold on. Oh, I was thinking the wrong thing.
So
You just need one
all you
more.
need to do
Yeah.
is to adjust it so that it.
Let's see.
So that when they're both on.
Mm-hmm. They're both on.
Off.
It's gonna be
It's
on.
off.
Yeah.
Okay. Okay, wait, I was thinking something different with that. Okay. Maybe this isn't gonna
Okay,
be
so
as
if
easy
they're
as I
both
thought it was
on, you
gonna
don't want it to go either.
be. So. Oh crap.
Well, right now you got everything except the last one, right?
What if
Yes.
you added like 2 more transistors before that inverter?
Then it's just gonna go. Then would just go back to the.
Yeah.
Yeah, you're right. Because we're not trying to.
That would no.
we're
That
just
would
trying
turn
to
it into like.
update it.
Yeah.
It's not an inversion; it's a negation.
Hmm.
So,
Okay, so one. Wait. Wait a second. Okay, I'm lost.
Yep. XOR's kind of weird.
Do we get hints or no?
I put up A naught and B naught up there for you. I
Yes.
left it up there for a reason.
There is a reason. Okay, great. No.
you're having fun with this, aren't you?
Easy.
Watching us struggle.
If it, well, this is how learning occurs.
Yeah.
Watching a bug on its back.
Now,
And just watching
One second. If it helps you any, you can draw the gates first. Compose an XOR with AND, OR, and NAND and inverted gates, because we already had the transistors for those. So once you make the gates, you can then translate it to transistors for you.
Right. Okay. It's true. Okay, yeah. Is
That's good, yeah.
let's see if this is an OR, this would be reverse of that.
No, it'd be 1 0 0.
And then basically you would need to AND these together. Yeah.
Okay. Wait, I'm
You-
following
you-
you. Yeah.
I'm not.
Draw the gates for that. Just draw the gates real quick.
So you would need to like AND and OR gate together, yes.
Yeah, draw the gates so I can make sure
Two
that
gates. Let's see.
you're going
Well,
with one solution, yes.
Okay.
It sounds like you're doing one of the solutions, yeah.
Yes.
Your not y has
So-
to be 1 0 0 0, not 1 1 1 0.
Yeah, he erased it so he could help himself look at it.
Yes. Yeah. No. This is going to be like a regular OR gate, and then this is the reverse of like the OR gate, which would be
The reverse
this-
of the.
Well, not a reverse. No, that wouldn't be why. No, why not would be okay. But this would be like if you did it in OR gate for A not and B
Here,
not.
hold on,
That's what I
stop.
mean.
Okay, hold on.
Okay.
I know what you're trying to do. You're,
And that's-
you're confusing yourself because of the way you wrote your truth table. This
Okay.
is the way to do it. Hold this.
Okay.
You want the output like this.
Yes.
What you're
Well, I
saying,
know that's
what
the
you're
next one.
saying is A, and then we'll just say NAND B, right? You can always write
Okay.
append to the truth table. That's fine. Is this right? So you got that with A NAND B,
No, that'd be OR B.
or B. I'm sorry.
Right.
Or yeah, or you're correct.
Or.
So go ahead and write that in there,
Oh, wait a
but
second.
leave
Or-
this alone. That way you see what's going on.
Okay. All right. A NAND B would be then, and then when you add these two together,
Mhm.
you get that.
Okay. All right, do it.
So let's see, NAND gate.
You already got the NAND. Already
Yeah.
got the.
I've got the OR.
You got the OR. Good. Let's leave
So let's see, a NAND gate would be.
Gate's literally back half.
Let's
It's
see,
just like 3 transistors, right?
round.
that. Which are you drawing the NAND?
Yes, the NAND. I'm drawing the
Okay,
NAND.
Yeah. So that's you already a little mini NAND up there.
He has a mini NAND, but he also has the OR.
Then-
Thank you. What if you just had the OR and then you attach a NAND on the end? Would that not work? Or have it feed into one of the
B.
two?
together.
See, so that is a NAND. This is an OR.
We gotta and them together.
Yes.
Send those two
So-
outputs.
So send the outputs to an AND,
You got it.
which is. Is there an easier solution?
There's always just write the AND gate. and
Okay.
Call it a day.
Great.
Okay.
And
Here,
then-
let me simplify this for you,
Okay.
just so life doesn't become complicated.
Oh.
We're gonna do this. Sorry.
Great.
Oh,
What?
bye.
Thank you. You got
Sure.
it.
Okay.
I don't know.
All right. Great.
Whatever. We don't need to do that again, do we? Anyone? Just rewind the video. Okay. So
Is
the
there an
what's
easier solution?
yes, but we're gonna go with this. I like this one.
And so you
Could-
take
could
the
it not
output of
have
the
been-
OR gate, right?
What?
That was the top part's the OR gate.
Yes.
There's the
Yeah.
output of the OR gate, and
The output of the OR gate.
And
So the
then-
output of the OR gate is 0, 1, 1, 1, 1 right over here. So this guy over here is going to be this column right here. So I'm going to put a star, and that's this guy over here. Okay, so that the voltage on that one is over here, right? This is a NAND, so let's call this box that's filled in.
Sure.
So then this is box filled in. Okay, box filled in and star going into an AND. So what it's saying is when you both are 1, then it's on. So notice 1 1 1 1 1 1 0 1 0 1 0 0. Okay.
I'm just gonna ask, what would have happened if you'd taken where the star is and you'd taken that wire and put it where the second A is on the bottom, and just
Okay.
had it feed into the NAND?
So then that would be over here. So you're saying star NAND B?
Yeah, I guess.
Okay, let's see what that does. So this is star, not, that's a star, here we go, star. So we're going to first
Yeah.
and B, so that's going to be 0, of course, and then we're going to not it, so that would be 1.
Oh, okay.
Yeah, it's not good. Good try. I like it.
I was
Well,
just curious.
maybe. Hold on, let's look real quick, just for the fun of it.
What?
1 and B. Oh, so it's on, so that's 1,
Would
but
it
you're
be
negating it, so that makes it 0.
literal reversal? No.
So then 1 and that, so that makes it off, and then it's going to be, yeah. So these are final 1 and
Like
B.
1 0 1 0.
Yeah, 1 0 1 0. Okay. Yeah, I don't think that's going to give you anything you want.
No, it's
No.
not.
All right.
So we have on the AND gate, we have 0 1 1 1 on one output, and then we have 0 0 0 1.
Wait, hold on.
All the way at the end down there, your inputs into your AND gate.
Down here? Oh, over
At the
here.
end. Your
Yeah.
inputs into there.
I'm calling it star and box.
And star is going to be 0 1 1 1.
Correct.
And box is going to be 0 0 0 1.
It should be. Shouldn't it be 1 1 1 1 0? Because it's not. Hold on, not A or B. So right, it's going to be 1 1 1 0 because only when A and B are on it is 0. Remember, it's negated and. You and it and then you invert it. So
The
1
gate
1.
AND is 0 0 0 1, right?
No, that's and.
Are you feeding the star in the box into an AND gate?
Yes.
Okay, so it would be like star is the one transistor.
Star is coming from
Box is
this
another.
whole OR circuit, and box is coming from this NAND circuit.
Okay, but what I was asking is if are they feeding into two separate transistors that are connected, and then it just goes to the output without the voltage resistor on the end, or is that not an AND?
Oh, you're talking about what the AND looks
Yeah,
like.
where the AND is at. Is it two transistors? One goes into one goes into the other, and they're connected,
to
and then it just goes to an output.
Yeah.
Okay,
Right.
that's what I was missing.
So here we go. Well, many more transistors. What's the saturation rate or time?
C. This an OR is 2.
All right. So to get the star costs 2. How about to get the box?
That's 1.
1.
And then
Those are
the
now-
and
The and
is 2.
is 2.
So overall, it's going to be 4.
Yeah.
Right.
Wait a minute, we got, but isn't one of yours in parallel? Doesn't matter?
Because the NAND and the OR are in parallel. So those are going to be saturating at the same time, but the NAND is going to get done first, but you still have to wait on
So
the
you go with the
OR.
longest path. then,
Yeah.
right?
Yes.
You always go
So you
long.
choose 4 then.
Yeah, it's
Yes.
4.
4.
It's 4. So our next OR takes 4. Yeah, it really usually takes 4. There might be. I have to look it up if there's a tricky way to do it with 3, but I'm pretty sure it was 4. So this is usually the one that comes with. Great. Any questions? Good. I think we're done with these slides. Good. Let me finish up the quick review. We did adding, we did a decoder, we did a mux.
Turn the projector back on.
Oh, the projector.
He's got to erase the board then too.
Making me do work.
That's what we're paying for.
We don't pay him anything. The school pays him.
Yeah, but we
But you
pay
pay the
school.
school,
said
which
that.
pays me. All right, where's the eraser?
It was.
It's right here on my desk. Thank you.
Nice.
Anyone else want to take a picture of this?
Nope.
No, it's
No.
good.
We got a video.
Yeah.
I'm glad y'all trust my videos.
Nope.
If you can get through all
Don't
the
worry, it's
laughing that I
not.
do throughout class.
If not, I'm gonna make you do this all day.
Thanks, Jonah. Okay. I think actually this will make more sense. Step over here. Or maybe we're not going to talk about them?
Nope.
No, we're not. Okay,
Who
fine.
needs to talk?
Okay. So I talked about propagation while I was teaching it, which will hopefully make this easier. Remember, data outputs do not exactly change when inputs do, so there is time over wires, which we usually say is roughly the speed of light. It's best to think of it as near the speed of light, so practically is,
What, 3 times 10 to the 8?
and that's in meters per second? Yeah.
Yeah.
Sure.
Yay, physics.
Yep. So everything has a propagation delay. I sometimes call it saturation. Did I say sometimes? It always does.
No, I'm just saying you always call it saturation.
Oh,
You're
okay.
like, what's the saturation? It's not.
Pretty much always.
Yeah.
So when you're looking at the gate delay, if you remember from our GTK wave, you could actually add the delay so you could see it moving.
Right.
When you actually go through your circuit,
Oh.
it'll show you how long it takes to delay. So as time moves on for this whole circuit to complete is, of course, the which path? Shortest, longest, average?
Longest.
Longest path. There we go. All right. So what is the cost here for this circuit where these G's are any type of gate?
What is the cost?
Yes, what's the cost of this circuit? Or not the cost, but how long does it take to complete? I usually call it cost, but when I say cost, it's what's the time for the circuit to complete?
3 times whatever.
What is 3?
Each of them max hour.
I had a lot of answers. Yes, Sydney.
What is 3?
3.
Well, depending on the gate they are.
Yeah.
Depends on the
depending on the
gates,
gate.
right?
Yeah,
Yes. So
so-
what is it really?
3 times whatever.
3
the
times
gates are.
N.
N?
No, because it could be different types of gates. So
Ah,
I said there could be any gates.
that's
all
frustrating.
Are you all tracking back there, Clea and Stephanie? Huh? You're just listening? What would be the longest path here? You don't know?
Not ready to take that step yet.
So either G2, G4, G5, or and like the cost of those added together, or the
18.
cost of G1, G3, G5,
Okay.
depending on
Would
which.
it-
Right. So it's the max
Yes.
of the cost of G2 plus G4 plus G5 or G1, G3, G5. You know, the sum of these three. It's the max of which one takes the longest.
trick question then. It was a trick question.
No, it wasn't. I just want
No.
you to come up with the right formula. Stop thinking of them in numbers.
Well,
Look,
technically-
it's not arithmetic anymore, man.
Technically, if we're looking for like the longest path, the longest circuit that we've made so far has been like 3 seconds or 4 seconds.
4
4
picoseconds.
So would you not do 3 times 4, and then it would be like 36?
Oh, so that's an upper bound. That's not the
Okay.
max. That's an upper bound.
Got
But yeah,
it.
I guess you could do upper bounds. Yeah. All right. Any questions about gate delay? I will ask you this at some point, like on your midterm.
Joy.
Okay.
So how would we answer that? We would say, it could be this or this.
Right. Right. You could just do this.
It depends.
So, oh, it's good.
Quick, take a picture of this.
So just,
Whoops. Yeah.
That's a
comma.
great G.
max of path 1 or max of path 2?
Right. Yeah. I'm going ahead and writing it all out to make sure that you all write it correctly in your exams. That last G always comes out as a 6. Right. So the max of the cost of the lower path or the cost of the upper path. Sure.
If we only wrote one of those, like if we only wrote like the cost of G2 plus G4 plus G5, would you count us off if we didn't add G1, G3, G5?
Yes.
Forgot your ending
Let's see.
parentheses.
Thank you, Lisp interpreter.
I mean, I'm just saying, if you typed that into a computer, it would have broken.
All the people at home who can't see it, there's the max cost of lower path, cost of upper path. All right. Any other questions? Okay. Let's go ahead and stop the recording. We're going to talk about memory.
Whoa.